addition, we have a brand new feature tonight. We have a guest from the Tucson Amateur Astronomy Association who will give us a brief talk about what's up in the sky right now. So this is a new feature we're adding. Once a quarter, we're going to invite our amateur astronomy folks to come and tell us what to look at when we look up at the sky. Okay. Oh, and also we have some handouts from the Tucson Amateur Astronomy Association up here at the front table with information about their events and about their group. So during the intermission, please feel free to come up and grab some of those handouts to learn more about what they're doing. Jeremy, can you go in and ask them to turn off the house music? Thank you. Okay. Also, during each talk tonight, there will be one trivia question or maybe more. When the trivia question comes up, please raise your hand. The speaker will call on you if you have a guess. And if you're right, you will win a very special prize. It's a SpaceDrafts sticker. But we also have a few other cool prizes that I snagged from a recent conference. Some postcards and some European Space Agency stickers you can choose from as well as for your prize. So mixing it up a little bit today. Finally, we have a tradition here where you may notice that we are right next to a very active train line, and it is almost a guarantee that we will be interrupted at least once by a very loud train announcing its presence. So when we hear the train whistle, what do? We raise our glass and we go choo-choo, and we take a drink to toast our guests, the train. Okay, so that's everything from me. My name is Logan Pierce, by the way. I'm your host tonight, and I am a grad student here at Stewart Observatory. Without further ado, I will introduce our first speaker, Griffin Hosenzada. He will tell us about explosions in space.
Thank you. Hello, everybody. Welcome to Astronomy on Tap. SpaceDrafts, whatever it's called. Both. It's both. Oh, wait, I need that thingy. Thank you. This is the most exciting title I could think of, Explosions in Space. I'm a postdoc at Stewart Observatory at the University of Arizona, and I literally study explosions in space. Today I'm going to tell you about how what does my life actually look like? How do we find these supernovae? And why would you want to even care about them? So first of all, some terminology. A supernova is an exploding star. You can see here an artist rendition of a star, and you can see it's just doing its star thing, and then all of a sudden, it explodes. This literally, I know you can't see the numbers on the bottom here, but literally it only takes a second for it to explode, and it will keep expanding like this for a long, long, long time, going from something that looks like a star to something that looks like this. Many of you have seen this image before. That guy has it on his t-shirt even. This is the Crab Nebula, which is a supernova remnant, meaning that this is like a cloud of gas that is left over after the star explodes. So this is like the material that was in the star, just kept expanding for a really, really long time, and it just made this cloud of gas. And this thing, there are already 2 trains. There's going to be another one coming here soon. Let's see if I can get through this slide. This thing is visible with a relatively small telescope. You can go out and look at it. It was visible, okay, I should have stopped now probably, right? I don't know what to do. Okay, choo-choo. Good thing I brought this up here. Cheers. Okay, so this is called the Crab Nebula. It's a supernova remnant that came from a supernova that happened in the year 1054. And the reason that we actually know this is an incredible story that's kind of an aside from the rest of my talk, but there are actually records from ancient Chinese astronomers that recorded the presence of a quote-unquote guest star, meaning that there was some point of light that suddenly appeared in the sky in the year 1054, and they even wrote down like exactly where in the sky it was. And if you look at, I don't read Chinese, but Wikipedia told me that that's what this says in the highlighting. If you go look at those coordinates now, you will see this thing there. And so you know that that was the star that exploded and became this. This is now 11 light years across, just to give you some idea, and it's still expanding. You can still observe it and see that it's moving outwards every year by just a tiny bit. So I'm going to zoom in on the very center of this here and show you what that looks like with some really awesome telescopes that we have. So this is a video, in a way, of the central region of that supernova remnant. On the left here is in X-rays. On the right-hand side is in optical light, so you could actually see the right-hand side with your eyes, if you had a really powerful telescope. And you can see that there is a little star still at the center there. That star is called a pulsar. It is basically the core of that star that exploded, just the very little bit that's left over. And it was, in the explosion, it got some rotation, and it's still rotating now. And it's very highly magnetized, and the magnetic fields around it are messing with all that ionized plasma that it ejected out there. So you can see kind of these like ripples going out through the gas there. It's really amazing that you can actually see this. And there's even, you can see it, the reason it's called a pulsar is that you can see it kind of blinking like this, especially in radio wavelengths. I could go give a whole talk about how crazy this remnant is, the pulsar that's left over, but let me continue. So that's what happens when you have a supernova in the Milky Way, in our own galaxy. But unfortunately, that doesn't happen very often, only like once every 100 years or so in a spiral galaxy like ours. So that leaves, my career is less than 100 years long, so I need to study other supernovae than the ones in our own galaxy. So that leaves us with other galaxies to look at. And other spiral galaxies have supernovae too. But that means we don't get as good of a look at them if they're so far away that they're in other galaxies. So here's a picture of a galaxy. There's going to be a supernova going off in it in just a little while, and see if you can spot it. Does anybody see it there? Okay. There are actually little tick marks, but I didn't know if you could see it on the projector. It is right here. And you can see suddenly just a point of light appears, and then it kind of slowly fades away. You can even, if you look carefully, you can see that initially it's very blue, and then it kind of turns to green, and then becomes kind of white, and eventually will become red at the end. So it does change color, as well as, increasing and fading in brightness. But unfortunately, this is all we can do, basically, is this picture. You don't get that beautiful artist's impression of a star turning into a giant nebula. You just have a point of light appearing in another galaxy, and from that you have to figure out what's going on. So the first problem is, did you see a star in that picture before the supernova came up? No. You just saw a galaxy, and suddenly a new point appeared. That's because that star that exploded was so far away that you can't resolve it individually, right? It's just one of those billion stars that was in the galaxy decided to explode. And we don't know when that's going to happen. The only way we know is by just looking at it and finding it. And the other problem is that even when we do find that it explodes, we don't know which star that was. And if you really want to use supernovae to understand something about stars, you kind of need to know what the star was that exploded. So these are kind of the practical challenges of studying supernovae in other galaxies. So first I want to tell you about how do we, the first point there, how do we actually go about finding a supernova to study? It's not easy. So the first step is that we have to just look at the sky all the time. I have a beautiful picture here of a bunch of small telescopes in Chile called the Prompt telescopes, which were the ones that we use in our supernova survey that we run at the University of Arizona. These just look at nearby galaxies. We ask them, they're all robotic. We just go on our computer and say, hey, look at these galaxies. They do that, and they send us the pictures back from South America. We also have one in Canada too, and one in Australia. But they're looking at the sky all the time. To give you an idea of what that looks like, you can imagine like a map of the sky in the same sense as a map of the Earth, where you can, have latitude and longitude, but on the sky. And over time, these telescopes will eventually look at a huge region of the sky. They can't look at, if they're in the southern hemisphere, they can only look in the south, and vice versa. But they'll cover a big portion of the sky, and they just look at there, every night or every few nights, depending on weather, etc. So then the question is, you've got all these images, way too many for a human to look at. How do you actually find a supernova in these images, right? Unless, you can hire 1,000 grad students and force them to look at a bunch of images, but you don't want to do that and they would get bored. So the next step is to look for changes. You actually take the image from today, you take the image from yesterday, and you subtract them from each other. Now this sounds easy, everybody can do subtraction in the audience here, I think. But subtracting images is actually a lot more complicated. You can see here, if I get this laser pointer working. So in this new image from today, there is a point of light here in this galaxy. In the image from yesterday, there is no point of light there. And if you subtract these, this image minus this image, you see there's just a point here. And this point is the kind of thing that a computer can find. If you have an image that's just like static and then a point of light, computer can notice that. But there's a problem, which is that there's also a supernova here, no supernova, but there's also all these other things in the image, which are just not real. They're kind of noise that comes from all these other stars in the image, and the computer also will find those. So this is not easy to do. We have to use pretty advanced statistical techniques called machine learning, which I'm not going to talk about, but I will talk your ear off about them if you want to later on. To distinguish between the good point of light, which is that one, and these other mess that surrounds the rest of the image. So anyway, with the help of computers, we can actually find these supernovae in real time by just searching every night and comparing the new images to the old images. This used to be done by hand, but no more. So then we found a supernova, but we want to actually learn something about it. As I said, all you can see from that image is, okay, something exploded, it got brighter and fainter. Getting brighter and fainter actually can tell you a little bit about it if you have some models, but the main tool we have in astronomy these days is spectroscopy, and the picture you should have in your head is taking the light from that supernova, passing it through a prism, and you get the colors of light that come out. I think many of you have seen this kind of rainbow effect before. But if you do it in a very detailed way, you can actually figure out what is the supernova, what is all that material that we see, the gas that forms the nebula afterwards, what is that made of? Many of you have seen the periodic table before, that's what you're seeing here, all the different elements that exist in the universe. Well, each one of those elements emits certain wavelengths of light. So you can think of this instead of just a periodic table with names, but you can think of it as like a table of wavelengths, where if you look for a certain color of light and a certain pattern of colors, you can then connect that to the elements of the periodic table. So for example, the first one, hydrogen, if you see just these specific wavelengths of light and no others, you know that you have just a giant ball of hydrogen and nothing else. If you look at our sun, for example, which is made of mostly hydrogen and helium, you'll see just these colors and these colors, which is helium, superimposed on each other, but you won't see very much of any of these other things. So like that is actually how we know that the sun is made of hydrogen and helium. So the problem is that you want to do all of this very quickly, right? So go back to this video that I showed you before. You notice that this explosion, it goes from looking like a star to looking like an expanding cloud of gas very quickly. The time scale here on this graph is like just a few minutes. So all of this whole entire video that I showed you takes like an hour in real life. So you got to get a spectrum pretty quickly if you want to understand what was the star doing before the supernova exploded. And luckily, we have these telescopes all around the world, robotic telescopes that we can control over the internet with our computers in real time. And we can say, even if it's not dark right now in Arizona yet. We have a lot of telescopes here, but we couldn't use them right now if we discovered a supernova. Plus, it's going to be cloudy in like an hour, so we wouldn't be able to use them today anyway. But one of these telescopes will always be in the dark here. You got the sun on this side of the Earth, supernova on this side of the Earth. One of these is always going to be pointed towards a supernova. This is just a picture of one network of observatories called Las Cumbres that I used to work with. But there are many other such observatories around the world that you can control robotically. And this is what we really need in order to get a spectrum of that thing immediately, right? To figure out what was the star that exploded. You kind of need to do that. And then once we do that, we announce to the world, we found this supernova. I know you can't read this, but this is actually a supernova that we discovered in our group at Arizona like a month ago or something. In fact, we discovered it and classified it. We're so awesome. These are the two reports that we send out. There's this website where you just say, okay, this and this coordinate, there's a supernova here, and this is the type. And we send in reports there very regularly, like once a month or so. So then, we announce it to the world. All the other astronomers that are interested in supernovae can follow it and get further data. We try to study it and figure out what's going on, which brings me to my next point. Why would you want to study these supernovae? What can you actually learn from them? The main thing, there's several main points. One is that the conditions inside a star when it explodes are like nothing that we have on Earth at all. So there's really extreme physics going on there that you just can't reproduce in the lab. And by studying supernovae and other things in space, we can understand these physics better. So to give you just an example, this is only one aspect of it, but to give you an idea of the energies involved in an exploding star, okay, I went too far. So, I'm going to introduce a unit to you. It's a metric unit. Don't be scared. It's a joule. This is a unit of energy. And to give you some context, a gallon of gasoline is like 100 million joules, right? So like a tank of gas in your car is like a billion or a couple billion joules. I'm not pointing it quite right. Okay.
I don't know what's going on.
One lightning bolt gives off about a billion joules of energy, 10 to the 9. If you're not familiar with this scientific notation, this is like 1 followed by 9 zeros, a billion joules. By the way, this is cool by itself, that like a single lightning bolt which takes just a fraction of a second gives off like 10, an entire car's worth of gas. That's pretty cool. Okay. The entire world produces, the amount of electricity that we produce in 1 year is 10 to the 20 joules. So that's like 1 trillion tanks of gas. That's a lot of energy. We're escalating quickly now. The amount of light that the sun gives off in a year is 10 to the 34 joules. That's like another 100 trillion times larger than the amount of electricity that we produce in a year. Okay, the entire Milky Way, our whole galaxy, which has like 1 trillion stars in it, roughly, gives off 10 to the 44 joules of just in light from all of those stars in a year. One supernova gives off about that much energy just as it explodes. So think about that. This is why when I showed you that picture of the galaxy with the supernova on top of it, you could see that supernova being so bright compared to all the other stars in that galaxy. Because really, the amount of power that supernova is giving off in that moment is almost the same as the entire rest of the galaxy combined. So this is really an extreme amount of energy. Could you imagine trying to do something like this on the Earth? It would not be good for us. Another point is that we want to understand stars for various reasons, including our sun, but other types of stars too. And supernovae are one way that we get to probe just the very end part of a star's life. Because if you think about it, stars' lifetimes are billions of years, or even more in some cases. So the chances of us actually seeing one in that final, last year of its life is very, very small. Most of the stars that we can see in the night sky are not close to the ends of their lives, just, by chance. They're somewhere in the middle of their lives, most likely. So if we want to really see those last years, which are the things that we understand the least, like right before they explode, what's happening, what causes them to explode, that kind of thing, we have to see these supernovae in other galaxies right before, we see that right after the explosion, which allows us to infer what's happening right before the explosion. The picture I'm showing you here is actually a star in our galaxy right here. Very, very massive star, a lot bigger than our sun. And it's producing this giant bubble of material around it. For some reason, we don't fully understand why that is. And we think this is the kind of things that stars do near the ends of their lives. We don't know exactly at what point before they die they do this. And we don't know exactly why, what causes them to eject this material. But we see things like this in our own galaxy, and then we see signs of this in supernovae that we study in other galaxies too. So this is really the only handle we have on understanding these last stages of stars' lives. These supernovae can even affect not only the star itself, but the entire galaxy full of stars. These supernovae can affect how those galaxies evolve. And if you stick around for the second talk, Mike will actually talk about this a little bit, I think, if you're lucky. The energy that these supernovae put into the environment of the galaxy will produce things like galactic winds. I bet you had no idea that galaxies had winds, but there is material being driven out of the center of this galaxy, partially because of supernovae, partially because of other things, but this is something that we would like to understand if we want to know, for example, how did the Milky Way end up looking like it does today. And just to give you an idea of the scale here, I know this looks like another fuzzy blob of material, just like that Crab Nebula I showed you, but that was, remember, like 11 light years across. This is like 37,000 light years across. So this is a totally different thing. This is a full galaxy full of a trillion stars. Okay, and lastly, the reason that we want to understand supernovae is that they actually, during that explosion, they produce a lot of the elements that we care about in our daily lives. So this is another picture of the periodic table that I showed you before, but it's color-coded by how these elements were produced. So you notice only helium and hydrogen were present from the beginning. They were produced in the Big Bang. Everything heavier than that, all the other elements in the world, were produced either in the course of a star's life or in the end of a star's life. So either they were produced during the nuclear fusion that stars do to produce energy, and even if that's true, that material only gets out when the star explodes, so supernovae are still important for that. And then the really heavy things are produced only in the explosion itself. So like, there's so much energy, I just talked about it for like 5 minutes, how much energy there is in a supernova, it actually does even more nuclear fusion and produces a lot of the heavy elements that you see here. So for example, humans are made of carbon, and other animals. The air that we breathe, the beer cans that we, I guess there are no cans here, but in theory, the aluminum, silicon that's in all of our electronics, the calcium in our bones, the iron in the railroad over there. I think I first gave this talk when the Olympics were on or something, so all these Olympic medals are here, and all the way up to uranium, which we use for power. These things are all produced thanks to supernovae. So, I will end with the question that everyone always asks me when I say that I study supernovae, which is a supernova going to destroy the Earth, like tomorrow? And the answer is no. And I'll continue now. The closest star that we know that is definitely going to explode as a supernova is Betelgeuse. It's this star right here. Many of you will recognize this constellation. Someone yell it out. This is not the trivia question, but there is a trivia question coming. This is Orion, and Orion's right shoulder is Betelgeuse. It's a red supergiant star. You can see, if you look with a telescope, you can actually see that it's much redder than the other stars. And it is going to explode as a supernova sometime, between tomorrow and like 10,000 years from now, or 100,000 years from now, or even more than that. We don't really know. The time scales of these stars are much longer than anything that we experience on Earth. This is a picture of it right now. It is very similar to that picture I showed you of the bubble around the other star, where there's a kind of a shock wave of dust and gas coming off of the star, and there's another one here. These are things that we don't really understand exactly how they were produced, and we'd like to. And in fact, one of the ways that we can get at understanding them is by studying other similar stars that explode in other galaxies. But even if this star does explode tomorrow, you don't have to worry, because it's like over 500 light years away, and that is far enough away that nothing that it does will really affect us. We will notice it, of course, but it won't cause any problems. It's not going to kill you. If some star within 25 light years or so explodes, then maybe we have problems, but there are no stars that we think will explode within that distance, so don't worry about that. If it does explode, it would be pretty amazing to see. It would be bright enough to cast shadows at night. It won't, it's hard to show a picture of what that looks like, but it would be very, very bright. You would definitely notice it if you were paying attention. So, my call to you as members of the astronomical community, please keep an eye out for new guest stars in the sky, because they could be a supernova in our galaxy, which would be like the most amazing thing that could happen in my career. So if you see something in the sky that's very bright, first make sure that it's not a planet, because those are also very bright. There's some story that my advisor told me that one of the Nobel Prize winners for supernovae actually made this mistake one time and reported a supernova that was actually Mars or something. So don't make that mistake, just double check where the planets are supposed to be. If you do find a real supernova, please email me with where you see it and what time it is. And if that turns out to be real, then I'll definitely pay for your trip to Stockholm when we win the Nobel Prize for all this amazing science we're going to do with the Milky Way supernova. So thank you. I'm happy to take any questions. Yeah, go ahead. Yeah, okay, the question is there a way to tell after the fact if you missed a supernova? If there was one and you missed it, but is there something still there that you could look at? The answer is yes, kind of. So think about that Crab Nebula that I showed you. Even if we didn't know, if we didn't have those Chinese records that there was a supernova at that position, we would still see that there was a supernova remnant there. Well, okay, so we would see that there was a nebula there. And if you take a spectrum, for example, of that nebula, you could see what kind of elements are present in there, and you could say those are the kind of things that are produced when a supernova happens. So you might infer anyway that that was the leftover nebula from a supernova. The problem is that that thing it wasn't big enough to see for maybe, I don't know how long, a very, very long time after the supernova happened. So you wouldn't immediately know. So the supernovae are bright for maybe months or so, maybe a year if you're lucky. And then you would see nothing for a long time, and then eventually maybe you could see a nebula, but that would be only in our own galaxy. Like in other galaxies, that's almost always impossible because it's just too small, too far away. Other questions? Yeah? Okay, so I can barely hear you because of the train, but I think you're saying, do the spectra of supernovae vary a lot between different stars? And the answer is yes. There are many different types of things, all of which we call supernovae, that come from various types of stars exploding. And I will pause here. Cheers to this train. I can't believe I thought those first two trains was going to be all, but we already got two more just in the first talk. Yeah, so I mean, essentially your question is what I was trying to get at here. If you're trying to figure out, based on the supernova, what star it was that exploded, one of the ways you can do that is by what elements appear in the spectrum of the supernova. Then you can kind of go back and say what elements were in the star and what elements would have been produced in the explosion of that star, and you can try to figure out what type of star that was exploding. Other questions? Oh, there's one there. But there's no chance I'm going to hear you. Okay.
I wish we had two mics.
Yeah.
So.
How come the nebulas aren't perfect spheres if they're just going into space, like in your model?
Yeah, that is an awesome question. I would say that is an active area of research, but the question is, why was that Crab Nebula not a perfect sphere? If it's just, a star that's then expanding out into space? There are many possibilities, and I think we don't know which one is the answer. One possibility is that the explosion is not symmetrical. So, for example, you could have like a giant chunk fly off to one side and not the other side. There's no reason to, we kind of assume they're spherical, but that could be wrong. The other answer is that space is not completely empty. There is material out around the star in interstellar space. So when a star explodes, the material is going to run into that material that's already out there, and it will be kind of slowed down slightly depending on the density that's around it. So that could produce something that is not perfectly spherical, but kind of depends on the ambient density around that star. Great questions. All of them actually were great questions. Okay, thanks very much.
All right, thank you, Griffin. That was really great. I learned some things for sure. All right, so now we're going to start a 20-minute intermission. It is 8:05, so we'll come back at 8:25. During intermission, please feel free to grab another drink. We also have up front information from the Tucson Amateur Astronomical Society, or Association, excuse me. And we also have something I forgot to say in the beginning. We have SpaceDrafts stickers for sale, $2 each. And we also have a tip jar. All of the money that you donate to us or pay for a sticker goes into us being able to produce more merch and more fun things for our audience. So if you'd like to support us, those two ways that you can. Also, you get a rad sticker for your laptop. Yeah, so we'll see you back here at 8:25.
We are unmuted.
All right. It is 8:25, so we are back. Hope you topped off your beers and topped off your mind for learning. I don't know, being dumb. Uh, now I'd like to introduce Jim Knoll from the Tucson Amateur Astronomy Association, our special guest of the evening, who will tell us what is up in the night sky right now.
All right, thanks, Logan. So yeah, as Logan mentioned, I'm Jim Knoll with the Tucson Astronomy Association, so we're the local astronomy club. And so I'm just gonna, this is the first time we've done this, but I'm going to kind of talk a little bit about what is going to be visible in the night sky for the next 3 months. Now, as you well know, in July and August is not our best time to be looking at stuff in the night sky. But once we get outside of the monsoon, obviously it'll be pretty good. So this might be a little bit of an eye test. It's probably smaller than you can see back there. Let me see it. So this is what, if we could see the night sky tonight, this is what it would look like when you look up. And normally what we classify as spring and summer are kind of galaxy seasons, and that's when we're really looking at galaxies that are in the night sky, looking for those supernovae that might be going off in other galaxies and things like that. And Virgo is a very popular constellation, and it is in the west right now and is about setting. So we're getting away from galaxy season and now getting into, in summer, we get an opportunity to be able to look into the center of our Milky Way galaxy with Sagittarius and Scorpius being up. So right now towards the south, let's see if you can see it at all. This is, let's see, find it here. Yeah, it's not showing up very well. Yeah, I think that is Sagittarius right there. But off to the south, when you look towards the south, you're looking in towards the center of our Milky Way galaxy. So if you've ever looked that direction and saw what we call the teapot with Sagittarius, and so if you can envision looking at the tea kettle, and I wish it would show up a little bit brighter on here, but it's just not quite showing up. That is the steam. If you were to look at the steam coming off the tea kettle, that would be like the center of our Milky Way galaxy. If you're some decent dark skies, you can actually see the band of the Milky Way galaxy arcing across the sky from south, basically south over to the north in the constellation of Cassiopeia. So that's there's all kinds of really cool things to see in Sagittarius and in Scorpius, because we are looking into the center of the Milky Way galaxy. There's nebula, there's star clusters, there's star forming regions, multiple star systems. There's all kinds of really cool things to look at. To the north, you can see a familiar constellation up here. This is the Big Bear, or Ursa Major, and the familiar asterism of the Big Dipper. So the handle of the Big Dipper is in the tail of the bear, and the bear right now is upside down. And we call these two stars right here, we call these the pointer stars. And they always point down towards the North Star, or Polaris, which is right here. Polaris is in the handle of the Little Dipper, and that is Ursa Minor, or the Little Bear. So everything in the night sky rotates around the North Star. So when you see long exposure pictures of star trails, what you're seeing is basically the camera pointed at the North Star, and as you keep the shutter open, all those stars arc across the sky when you're looking at that. Straight overhead right now is, if it will show up here or not, is Hercules. And so right straight up, and when you look at Hercules, you can actually see there's a really cool globular cluster, what we call it. So that's M13, or the Hercules cluster. And that is a cluster of very old stars in the Milky Way, several 100,000 stars. And when you look at that in a telescope, you actually see a ball of stars. Now, if you think about it, the nearest star to our solar system is 4.2 light years away. The average distance between stars in a globular cluster is about 0.1 light year away. So you would have a sky filled with stars. All right, so that's pretty much it for July. We are just now getting some planets coming up in the east. So right there is Saturn. Saturn is starting to come up in the evening sky. And if you haven't ever seen Saturn or Jupiter through a telescope, it is absolutely critical that you do, because you can clearly see the rings of Saturn. You can see several of its moons. You can see the ball of Jupiter. When you're looking at Jupiter, you can see several of its moons. And those planets are now migrating back into the night sky. So in August, everything's rotated around a little bit in the night sky. So Ursa Major's kind of rotated down here a little bit further. Virgo is set, and now in the straight up we have the constellation of Cygnus the Swan, and Cygnus, the very head of Cygnus is a double star called Alberio, which looks really cool in a telescope. You can actually see the different colors of the multiples of the double star. And so this is Cygnus, and it's also called the Northern Cross. So if you look up here, this would be the up and down portion, and this would be the cross piece of the cross. And if you look carefully, you can also see what's called the Summer Triangle. So this is Lyra. So this is the Vega up here, and then down to Deneb, and over to Altair, which is in Aquila the Eagle. And so that right now is in August is pretty much straight up. And so that's a really cool thing to be able to see, and that's called the Summer Triangle. And then again in the evening, we have more planets coming up. So not only do we have Saturn, but we also have Neptune and Jupiter coming up. So in this fall, when we start doing star parties again, and we usually take the summer off because we just, with the clouds and everything, we just can't get them in. So in September, when we start doing star parties again, we'll have Jupiter and Saturn in the evening sky, and they'll be really, really awesome to look at. And then in September, everything rotates around a little bit more. We're getting into some pretty cool things coming up. Over here in the towards the north, you're going to see, can't really tell if I'm pointing, but right in this area will be what I call the court, or you'll have Cepheus the king and Andromeda the princess, and in between the two will be Cassiopeia the queen. And so they're kind of watching over each other. One of the things you can see in the night sky, most everything you see in the night sky is within the Milky Way galaxy, with the exception of the Andromeda galaxy. And that's the furthest thing you can see with your naked eye. So if you're in a dark sky, you can actually find it by using either Cassiopeia, or you can look at the Great Square of Pegasus, which is just coming up in the east, right in this area. And you can use that to find Andromeda, and you can actually see that. That's the furthest thing you can see with your naked eye. So, for us in the summertime, it's not so great to be able to look at the night sky. But once we get into September, things will start picking up again. So I hope you guys do come out and check out some of our events. We, like I said, we normally do take the summer off. I have a list of star parties up here, so if you want to grab one of those, it'll tell you what's coming up and a little bit about the club. We have a lot. These are all public ones. We do frequently at Canoa Ranch down south of Tucson, Agua Caliente on the northeast side, Catalina State Park, and the Chiricahua National Monument. We actually do an event out at our astronomy complex near the Chiricahua Mountains, so that's an opportunity for you to see some really cool stuff and do some dark skies. And we also do a virtual star party, so we have several telescopes that we hook up to and stream to our YouTube channel to be able to do virtually. So that's kind of what we got coming up. There's our website is right there, and that'll give you an opportunity to get more information. All right, thanks.
Thanks, Jim. All right, just give us like 1 minute to switch over the presentations. What happened? Where'd it go?
I think it's still stuck.
Well, can you just like?
Yeah.
I don't know. That's weird. Okay. Let's just get rid of that. Yes. What happened over here? I don't know what happened. That's weird.
Where you like froze or something. Oh.
There we go. What? Cancel. Okay.
There we go.
Play. What's happening? There we go. Okay. I don't know what happened.
I think you're just stuck.
Okay, let's do the, there's my mouse. No, but like, where is it though?
I think it's maybe just on the other.
No, I've been
screen.
going like this.
Down
There it
other.
is, okay. Window capture.
Yeah.
We can find a more graceful way to do this. All right.
Cool.
Okay, and then PowerPoint in the foreground. There. All right, thanks for your patience there, folks. We had a little technical difficulties, but we're back on track. And now I'd like to introduce our final speaker of the evening, Mike Jones, who will tell us about oases in a desert.
Okay, hi everybody. So I'm Mike. I actually work in the same research group as Griffin, who is our first speaker. But unlike Griffin, I don't study individual stars. I study some of the smallest galaxies, so collections of stars, and also some things that are not quite galaxies, that I'm going to call stellar systems. And I'm going to explain exactly what I mean by that in a minute. But I want to talk to you about these objects that we sort of nickname blue blobs, and you might be difficult to make out if you're in the back, but there's these blue clumpy things that you see in these images here. These are Hubble Space Telescope images, and we think these are a completely new type of stellar system that we just recently discovered. And so I'm going to tell you a bit about those today, and about why they're exciting objects. So although those pretty pictures that I just showed were from the Hubble Space Telescope, and that those are optical images, invisible light, this story didn't actually start out like that. So we didn't start out with the optical images. So if I start at the beginning of the story, this type of object was something that was discovered almost completely by accident. So collaborators of ours were mapping the sky with the Arecibo telescope. So this is a radio telescope in Puerto Rico. And you may actually have seen on the news that about 18 months ago this telescope unfortunately collapsed. But the survey that was being done with that was finished by then, fortunately for us. And this is really just a mapping of the sky. You know, like when you look on your phone, you have Google Maps, and it has satellite mapping of all of the ground on the Earth. Well, we as astronomers kind of do the inverse of that. We blindly map all the things that are in the sky. And this is a really good technique if you want to try and find things when you don't really know what you're looking for. If you just map the sky, then you can find all sorts of weird things. And this particular survey was done in the radio, and one of the things you can see in radio emission is gas clouds. So our collaborator was looking for gas clouds that were near the Milky Way, near our own galaxy, and then trying to find stars that might be in those gas clouds as a way to identify some of the smallest, nearest galaxies. And one of these objects, one of these gas clouds, did indeed have stars that you can see in this image here. But when this was followed up with the Hubble Space Telescope, you get this image here from Hubble. And unfortunately you can't see this super clearly on this screen, but this object is resolved into lots of individual stars, and it's actually much further away. It's not something that's near our own galaxy at all. It's something that's about 50 million light years away, in something known as the Virgo cluster. So our previous speaker was mentioning that Virgo's a constellation, but there's also a galaxy cluster that's in there that I'm going to talk about in a minute. And that's where this object is. It's embedded in that galaxy cluster, but it's just a tiny clump of really blue stars. And blue stars mean that they're young, and it's split up into two bodies here. There's other stars up here that are probably difficult to make out. And it's a gas-rich and it's an isolated object. And all of these things make this object very weird, and it doesn't belong there. And I'll explain it, through the talk why all of these properties make it quite weird. So this was the first blue blob that was detected, and as I said, this is a stellar system, not a galaxy. What do I actually mean by stellar system? So that's kind of a very generic term. So I'll give some examples. So you can have just a binary star, two stars, like this famous example from Tatooine, and you can also have a star cluster, a small cluster of maybe dozens or hundreds of stars. You can have a big star cluster that's thousands of stars. And then usually by the time you get up to a galaxy, you're talking about millions of stars. But this is not just a distinction of the number of stars. And the objects that I'm talking about now they fit sort of on this line where it's sort of borderline between what's considered a galaxy and what's considered a star. A star cluster. And so I'm going to start with my first trivia question next. I think it may be a bit tricky. If you're over there, I don't think you're allowed to answer, but it's a quite tricky question. And don't worry about putting your hand up first. I'm going to give you a chance to raise your hands, and then I'll pick someone randomly. So my question is, what does a galaxy have that a stellar system doesn't? Okay, so I'm going to go through the options. So the first option is just many more stars. Second, option B is gas and dust. Option C is dark matter. And option D is planets. Okay, so many more stars, gas and dust, dark matter, or planets. So, yes, this guy in the blue. Sorry, I can't hear you. Okay, yes, so he says dark matter, which is indeed correct. So, congratulations, I think you get a sticker or something.
You get a sticker prize at the end.
Okay. Yes, so all of these other things are actually things you can get in star clusters. It's not just a number of stars that distinguishes a star cluster from a galaxy. You can have a really, really big star cluster that might have hundreds of thousands of stars, or a really tiny galaxy that has a similar number of stars. And indeed, young star clusters often has gas and dust in them as well, but or planets. And the key thing is dark matter, and why that is because if you have a star cluster, then you can look at the orbits of the stars around the star cluster, and you can explain all of that just from the gravity of the other stars. But if you look at a galaxy, it's a fundamentally different object, because just the mass from those stars doesn't explain the motion of the object. You need something else, which is this dark matter. So that's really the distinction between a stellar system and a galaxy. Okay, so I mentioned that this first object that we found was in the Virgo cluster. So this is a cluster of several thousand galaxies, and this is just sort of a montage image where everything that isn't a galaxy in the cluster has been removed, and so these are all just galaxies that are in the cluster. And as I say, there's several thousand, and this cluster is an enormous structure. It's about 10 million light years across, and it's at about 50 million light years away from us, and so that's actually the nearest cluster. So this is made up of lots of galaxies, but there's also a lot of hot gas in this cluster. So if you take an image in the X-rays, so this is an image from an X-ray observatory that was in orbit, then you see this bright sort of fuzzy orange stuff, and what that is really hot gas. And this whole cluster is filled with this hot gas. And when I say hot, I mean millions of degrees, so seriously hot. And if you're a galaxy, a normal galaxy like, say, our Milky Way, and you want to continue forming stars, what you need is cold gas. And by cold there, I mean way, way, way below zero. And so these two things don't really go together. And when a big galaxy, even a big galaxy like our Milky Way, falls into a galaxy cluster, it very quickly loses its gas and can no longer form stars, because that cold gas is what you need to form new stars. And this is why most of the galaxies in this image are sort of orangey or red. It's because they're not forming stars. So new stars are generally blue, and so these galaxies are filled with old stars, and they're not forming any new ones. So basically, this galaxy cluster is a really, really hostile environment to star formation and cold gas. And so I'm gonna, for the purpose of my metaphor of oases in a desert, which is the title of my talk, this is the desert. Okay, this galaxy cluster that's filled with this hot gas, it's the desert. Okay, and as I said, even a pretty massive galaxy like our Milky Way, its gas can't survive very long, and it stops forming stars pretty quickly once it falls into a galaxy cluster. But this tiny, tiny thing that I showed you a few slides back is way, way smaller than our galaxy, but it has all of these young blue stars in it. So what's it doing there? And what formed it? How did it get there? So that's kind of why we find it intriguing, and why we're trying to figure out what it is. Okay. So this is going to be tough, I think, with the images, but okay. So we had this one object, okay, and we wanted to see, is this thing just something really, really weird? Is it a one-of-a-kind enigma, or are there other objects in the cluster that are similar? And the way to find that, unfortunately, when you have a sample of one, and it's this really peculiar, clumpy kind of object, there's not really a good way to find them other than just looking for them with your eyeballs. So that's what we, mainly my boss, who's over there, did to try and find these. So I'm going to show you some images. This is from another survey that maps the sky. This is called Decals. And this maps a large fraction of the sky, also in optical light. And this image actually has one of these blue blobs in it, but you probably can't see it. So we're going to switch to the next image, which is a much, much deeper image, which is also an optical image, but it's just the exposure is longer, and so it's much more sensitive. Okay, so maybe now someone can see the blue blob. Do you want to someone raise your hand if you can see it? Yeah. Do you want to tell me where it is? Yeah. yeah, up top. Yeah, so this is, for those that haven't seen it, it's up here. So this is just this clumpy structure of blue stars. Okay, and then there's one more trick that we have up our sleeve, which is that there's also, this really doesn't show up, sorry, but there's also another survey which looks at ultraviolet light, and young stars also give off a lot of ultraviolet light. And so I promise you that you can see this object very clearly at the top of this image if you look at it on a computer screen, but sorry, it didn't come out. Okay, so this was that was the example, and now's the test. Okay, so this time I will be looking for the first hand that I see. Okay, so this game's pretty simple. One of these 4 images is going to have a blue blob in it, and it's kind of a tough one. But one of these images has a blob in it, and the first person to raise their hand and tell me which image wins. Okay, so yeah, you back there. Which one? Sorry, I can't hear you. Yeah. Okay. It is indeed B. Yeah. So there's congratulations. Yeah. So there's two clumps here actually. There's one clump down here and another little bit up here. This is actually the same object that I showed you at the very beginning. Is this the first blue blob? So congratulations for finding that. Okay. So back to our story. Oh, this is just a larger version of that image. Okay, so back to our story. So we looked for these, just looking at thousands of those images like that, and we found 5 of them. And then this is an HST, a Hubble Space Telescope image of one of them, and you can see this clumpy blue structure. So these are all star clusters. There's also a few up here, stars and star clusters, and they're all young and blue stars. So that's what these things are made of. They're completely dominated by those stars. And so that's kind of a conundrum of how these tiny things that just have blue stars are in the middle of this desert. So this is our oasis, our collection of young stars that's in this desert. Okay, and most of these other things, just if you're curious, most of these other things in the image are background galaxies. They're not associated with this object at all. These objects are actually incredibly isolated. So down here, I'd say that they're at least 200,000 light years away from the nearest galaxy that they could have plausibly come from, or plausibly be associated with. So these are really just tiny things that are out in the middle of this cluster. And so we wanted to try and find out more about them. And so we had sort of a 3-pronged approach, looking at three different things for these objects. So I've already shown you lots of Hubble Space Telescope images, so that's really the best thing, except for now JWST, but at the time this was the best thing for studying the individual stars in these objects. So that's where most of the images that I showed you of them come from. And we also followed up with the Very Large Array, which is another radio telescope in New Mexico. And this is really good at detecting the gas in these systems. And actually most of the objects, it turns out, don't have much gas. So we didn't detect 3 out of 5 in gas. And then finally, we used this Very Large Telescope in Chile. That's literally the name, Very Large Telescope. This allows us to look at those star-forming clumps, and we can detect, as Griffin was saying, when you take a spectrum of those kind of clumps, you can detect what elements are in them. And so this is what I'm going to talk about for the remainder of the talk, really. So you can find what these things are made of, what's in their gas. And so this slide's a little bit complicated, but I'll go through it. I'll go through it all. So. As I said, this tells us these observations. They tell us what elements are in the gas of these objects, and as a normal galaxy builds up its stars, as each one of those stars explodes, as Griffin was describing, that spreads new elements out into the galaxy. So as the galaxy gets bigger, each generation of stars makes more heavy elements. And so the number of heavy elements is what we call metallicity. So these are normal galaxies, these grey and white points. And so as the galaxy gets bigger, it gets more more heavy elements in it. So this trend is what you see for a normal galaxy, okay? And so we measured for our objects these blue blobs, and we see where do they fit on this. And the answer is they don't fit this relation at all. They're these things up here. So they're completely different from this relation. They're not like a normal galaxy at all. And because they have a lot of heavy elements, but they're really small. This, if you've seen these many times before, this is kind of a telltale sign that these objects formed from gas that was stripped from a large galaxy. A galaxy that had already built up lots of heavy elements, just a chunk of gas was taken out of that galaxy, and that's what formed these objects. And there's two ways that you can do that. So these other systems that are up that sort of look pretty close to our blue blobs are what are called tidal dwarf galaxies. And the way that they form is when you have two galaxies that pass nearby each other. So I'm going to move my hands and try and not drop the mic. So if galaxies move past each other, they can interact gravitationally and pull their gas out into these long tails. So that's what's shown here. There's a pair of galaxies that are merging here, and then there's these two long gas tails that come out from this galaxy. And if you have very if you have
Train 5? Is the fifth one? It's a lot.
Something like that.
Okay, I think I'm good. So if you have very dense clumps in these gas tails, they can collapse to form something that looks like a galaxy, and that's called a tidal.
Really fun. Jeez.
Okay. Yeah, okay. So I was saying that when you have a very dense clump, it can collapse into something that's called a tidal dwarf galaxy, where it starts forming stars. So that's one option that you can use to form an object that's similar to what we have. But there's also another option, which is called ram pressure stripping. And so ram pressure stripping. I'm now going to really badly mix my metaphors, so I apologize for that. But so the thing that I was calling a desert, I'm now going to call a swimming pool. So it's a little bit different, but you have to use the analogy that works in each situation. So what's happening here is this galaxy cluster is filled with all of this hot gas, okay? And before I was saying that was the desert, but now this hot gas, I'm gonna want you to picture it as a swimming pool, okay? So it's like a big thing that's full of lots of water, okay? And that water represents that hot gas. And when you have a galaxy, say something kind of similar to our Milky Way that's got lots of its own gas, when that falls into the cluster, it's like you belly flopping into a swimming pool, okay? And that all of the gas that's in that cluster smacks really hard into the galaxy, and it forces the gas that's already in the galaxy out behind it. So that's what you're seeing here. You have kind of this bow-shaped structure of the gas that's in this galaxy, and it's being pushed back out of the galaxy. Okay, so that's actually how the cluster removes the gas from the galaxy. And what can happen is, again, you can have clumps of this gas that are in the wake of this galaxy, and they can also collapse and start forming stars. So that's another way that you can create an object similar to what we're talking about. But in both of these pictures that I've shown you, you make something that's right next to this big galaxy. And that's not what we have. We have these really tiny things that are in the middle of nowhere in this cluster. They're not near any big galaxy. So how can you do that? so this is kind of where there's a tiebreaker between these two mechanisms. So the tidal dwarf galaxies, that was the first scenario where you have the two galaxies passing nearby each other. When you form one of these objects that way, it's usually ejected from the system at fairly low velocity. And when I say low velocity, I mean low, sort of astronomically speaking. So this is 400 kilometers a second, which I guess is like 250 miles a second or something. And so that's pretty fast, but astronomically terms, it's not actually that fast. Whereas, so in order for an object, one of those objects, to become isolated, that takes billions of years. And by the time it's billions of years old, it's not going to have all these young stars that we see in it. So that doesn't really work. Whereas if you have this ram pressure stripping model, really the only thing that's determining how fast it can escape then is just how fast that galaxy falls into the cluster. And that can be really, really fast. So easily over 1,000 kilometers a second. And so in this scenario, you can get one of those clumps that gets really far away from your galaxy, like 1 million light years perhaps, really fast. And so that's a much better way to allow them to be isolated. And this is just a simulation, it's kind of an old simulation actually, of a galaxy that's being really forcibly ram pressure stripped. So this is the galaxy, and then this is all the gas that's been ripped out of that galaxy by this interaction with all the hot gas in the cluster. And then in the simulation, there's actually stars that are forming at the very tips of this tail of gas. And so these are the kind of things that we're probably seeing are our blue blobs. Okay, so that's pretty much it. I'm just going to give a summary. So as I said at the beginning, we think these are a new type of stellar system. Nobody's ever seen anything quite like this. And there's kind of three reasons together, combined, that make these objects unique. So the first is that they're these tiny systems and they reside in a galaxy cluster. They're also isolated. They're not like right next to any big galaxies. And they're completely full of young stars. So those three things combined make them unlike anything else. And in terms of how they formed, as I said, they have a lot of heavy elements, which really indicates that they must have formed from a much bigger object, and the gas was stripped from that to form them. And the most reasonable mechanism to do this is ram pressure stripping, and that's really because that's the only way you can explain that isolation. So I just leave you with these images that from the Hubble Space Telescope of these objects, and then I'll take any questions.
Sorry for the feedback. I have a question. Can you go back to the last slide? So if you have these, in the simulation, you have all this gas that's kind of connecting the galaxy from where the new stars are forming. Can you search for that gas trail to like kind of confirm this?
Okay, so the question for those that couldn't hear, if you have this in this simulation, you have this gas tail that's connecting the sort of parent galaxy to these blobs at the end. Can't you search for this gas? So the answer is yes, you can. So there is actually one of these objects where we do see this gas trail, and it's around 200,000 light years long in that case, and we can just still see that connection. But as I said, 3 out of 5 of the objects, we don't detect any gas in them, and so probably they're a bit older than this scenario that we're seeing here, and most of that gas, because it's embedded in this really hot gas within the cluster, most of that gas has since dispersed and become ionized, and we can't see it anymore.
Just to help the whole projection, what speed is Earth traveling at?
What speed is Earth? Okay, so I think Earth is like, I'll repeat the question again. He was, just for reference, he asked what speed does Earth travel at? So I think Earth is about 30 kilometers a second. So that is way slower than this. But Earth is just a planet that's orbiting a star, right? And so the sun orbits the center of the galaxy at about 200 kilometers a second. But velocities for entire galaxies, they can be much larger than that quite easily. Okay, so that's a great question. So he asked if these gas clouds are traveling through this the intercluster median, this hot gas. These gas clouds are really cold themselves. So how can they be in equilibrium, and how can they survive to get so far away? So that's a question that I don't actually have the answer to right now. So this simulation, as I say, is it's kind of old. It's over a decade old, and sort of the latest simulations of this process, they don't really show the kind of objects that we see, and so there's probably something missing. There's some physics missing from those simulations. There's something that's not quite right, because it doesn't make these kinds of objects that we see. So I don't have a completely good answer for you, but it's possible. For example, that there's actually pressure that's exerted from the hot gas that compresses the cloud, and that can help it maintain equilibrium and survive longer. But yeah, it's really active research at the moment. Yeah, it's very turbulent. Yeah. Oh, what? Oh yeah. Okay, so the question was, do we expect to see the blue blobs evolve with time and become more red? Do we expect to see them? So the answer to that is probably not, because although they are certainly going to evolve and become more red, there's kind of two problems. So the first is, right now, even with the Hubble Space Telescope, the only stars that we're seeing are the biggest, bluest stars. So when those stars die and you're left with fainter, redder stars, you're going to see nothing. And the other problem is that, so as I said at the beginning, I called these stellar systems, not galaxies. And one of the reasons for that is we think that after they lose their gas, they're no longer going to be gravitationally bound. So those clusters of stars are going to spread out into the rest of the cluster. And so then they will be almost indistinguishable from everything else. Okay, so he asked if we're going to use any images from James Webb Space Telescope. So we don't have any images from James Webb, but that is definitely something we are going to ask for in the future. So fingers crossed, we will get James Webb images. And one of the real advantages that you can get there is, so as I was just answering the previous question, we're only seeing the brightest, bluest stars. But because James Webb is so much more sensitive than Hubble, we'll be able to see the entire stellar population, much fainter stars that make up most of the stellar mass of these objects. I think that's all then.
Thanks, Mike. That was really interesting. All right, well, that does it for SpaceDrafts 78. I can say that after tonight, I certainly understand hot gas in the desert. Thank you for braving this ridiculous weather we're having. We will be back next month on August the 16th. We are here on the third Tuesday of every month, same place, same time, 7:30, Borderlands. You can follow us on Facebook and Twitter. You can also join our mailing list to get our newsletter into your, not newsletter, but show announcements in your inbox. We still have stickers for sale. Don't forget to tip your bartender. What else? If you won one of those trivia questions, please come up and get your prize at the end. And I think that is it for me. So have a great evening, have a safe drive home, and we'll see you in August.